Well, hello everyone and welcome to this webinar. We will start in a moment, but before that, please keep your microphone and camera off during the presentation. And at the end, there will be a 15-minute session for questions. Now, Professor Gabriel Merino from Simvestab Mérida will introduce our speaker.
Gracias, Jessica. So, please let me introduce Dr. Triana. Johan Triana graduated in physics. Graduated in physics at the Universidad Industrial Santander in Bucaramanga, Colombia. And he did his master and the PhD in physics at the University of Antioquia in Medellin, Colombia. And he's currently doing a postdoctoral state at the University of Santiago de Chile in the Dr. Felipe Herrera groups. So it's really nice to have a Johan. So please, Johan, el público es tuyo.
Okay, thank you. Before to start, is there anyone that doesn't speak Spanish in the audience? Just to give the talk even in English or in Spanish?
Creo que todo el mundo habla español, pero si quieres darle en inglés, no hay ningún problema. Adelante, como tú gustes.
Okay, no problem. Thank you, Gabriel. My name is Johan Triana, and I'm postdoc at the Universidad de Santiago in the group of Professor Felipe Herrera. And thank you for the invitation in this event to the Red Latinoamericana Physicoquímica Teórica. Today, I will speak about my research of a few years, which is based in Polariton chemistry, especially in the strong and ultrasound coupling regime. And I will talk about the spectroscopy of this hybrid light matter hybrid system and the dynamics or photodynamics in the systems. The outline of my talk is the following. It will be split in two different parts. The first part is an introduction, motivation, how the field, the research field have evolved from atoms to molecules, coupling atoms with quantum fields to molecules coupled to quantum field, especially inside cavities. Second, I will speak about Polariton chemistry at infrared regime, where experiments are performed mainly in Fabry-Perot cavities, and also the theory that I have developed here in Santiago. And finally, I will speak about Polariton chemistry at visible regime, where the key point here is it's to coupling between two different electronic states of a particular molecular mode. And in this case, this work has been mainly performed in Colombia with my PhD advisor. Okay. First of all, cavity QED with atoms. It's a field where the most common model to describe this kind of system is the James Cummings model, which was developed in 1963, and where the Hamiltonian, the simple Hamiltonian of the system consists in the energy of the atomic level, which has only two levels are considered. The energy of the cavity mode, the quantized mode of the field inside the cavity, represented by the photon number operator, and the interruption Hamiltonian, considering in this case the rotating wave approximation, where the counter-rotated terms are neglected. In this case, both subsystems, I mean the atom and the cavity, interchange energy, especially if we are in the strong coupling regime. One of the features that we can observe, or to ensure that we are in the strong coupling regime, is that in the experiment, or if we calculate the spectrum of this complete system, we will have, or we will obtain a splitting between these two peaks where the separation between them is the Rabi splittings, which define the rate at which these two subsystems interchange energy, which is usually known as the Rabi frequency. In addition, for example, if the cavity initialized in a different quantum state of light from a Fock state, for example, if the initial state is a coherent state with a defined mean photon number, will we observe the well-known revivals of the population of the atomic level? And all these theoretical predictions from a few decades ago were confirmed along the years in different experiments around the world. Okay. However, the main point here is that we only have two levels, and with only these two levels, we interchange energy with the radiation mode or the field mode. If we move to cavities, there are several experiments right now around the world performed, especially in the last decade, in the group of Stefan Kena, group of Thomas Eversen, Stefan Bomber, Timo Shigai, and in the visible region, the main systems are dielectric microcavities, where the mirror consists in dielectric are filled with dielectric materials, and the molecules are inside these two mirrors. Another plasmonic nanocavities and metal microcavities, and I mentioned before. The key point here is to couple two electronic states. However, if we go to the infrared region, experiments at this part of the electromagnetic spectrum is performed especially in Fabry-Perot cavities, where the molecular modes of the molecules that couple with the field inside these cavities is usually a microfluid inside these cavities. And these experiments right now are performed in the group Thomas Sevensen and Blake Siskin, and they're obviously in Abel in USA. However, what is the change with an atom to move from an atom to a molecule? Okay, consider that we have or that we select a particular mode, I mean electronic or vibrationally, of a mode. In this case, from the hexacarbonyl, I select the carbonyl mode. And what happens if I put inside the cavity and couple this mode with a particular mode of the cavity? Okay, we will obtain almost the same that in the atomic case if we consider only the two first vibrational levels of the molecular mode. Will we obtain the splitting, which are represented by these two states that are known, especially which are known as the lower polariton and upper polariton, and also we can consider more Fock states. However, if the mode is vibrationally, there is no limit to go beyond the first excited vibrational level. We can include more vibrational levels. We create more polariton states. These states are the hybrid states created or generated by coupling light and matter here. Okay? This is the main change moving from atoms to molecules. Now, what happened, or why this research is interesting, is because we can modify chemical reactions, putting all the reaction inside the quantum cavity. First, to have a comparison point, I will explain in a few words the picture out of cavity. Consider that we want to make this reaction, this chemical reaction. We consider an inner solvent, which is the ethyl acetate, that excites these carbonyl modes or activate this carbonyl mode, which interacts with the fluorion, and at some point the fluorion helps to break the bond and we obtain these two products. From these reactants, we obtain these products at a specific reaction rate, which can be measured in the experiments. Now, if we put all these components inside the quantum, inside the cavity, and boil the cavity in a way where the carbonyl mode of the ethyl acetate and the carbonyl bond of the solvent is on resonant with one of the modes of the cavity. I mean that one of the frequency modes of the cavity it's on resonance with this carbonyl bond. If we do this and measure again the reaction rate, we obtain that the reaction rate increased, accelerating the chemical reaction that we want to do. Note that the empty blue circles define the reaction rate out of the cavity. And what happened, for example, even if instead of use the ethyl acetate, we use an isotope of the ethyl acetate, we don't have any reaction rate. We don't have a chemical reaction is not performed even inside or outside the cavity. Using an isotope means that we move this peak, the frequency of the carbonyl mode of the isotop, and as a consequence, it's not resonant with one of the frequency modes of the cavity. Okay, this experiment was performed even just 2 years ago. Okay, with this introduction, I want to start explaining the Polariton chemistry at infrared reading, especially anharmonic vibrational polarons. As a theorist, the first thing is to define a model to represent or to describe the system that we want to describe the system. The model that we employ is known as the multilevel quantum Rabi model. It was developed here in the group of Professor Felipe Herrera in Santiago, and has three different parts: the molecular Hamiltonian, the Hamiltonian of the field, and the interaction Hamiltonian. In this model, we describe the molecular mode, the potential of the molecular mode by a Morse potential. And why a Morse potential? Because we can take into account the anharmonicity of the system, and also we can consider both bound and unbound vibrational levels in the model. We can consider or to describe even dissociation effects of the molecular mode in these hybrid systems. The cavity mode is described by the harmonic oscillator, and their vibrational levels are the well-known Fock states. And if we put these two modes in interaction and diagonalize all the complete Hamiltonian of the system, we arrive to the anharmonic vibrational polaritons. But what is one polariton? One polariton is the superposition of the direct product of the bare direct product between the vibrational levels of the molecular mode and the Fock states. In other words, we can see these anharmonic vibrational polaritons as if each photon number has a complete basis of the vibrational levels. The point here is that, for example, the dissociation threshold in energy for a photon number or for a Fock state different of the vacuum state is above the dissociation of the usual dissociation threshold, and as a consequence, maybe here in this kind of system, the dissociation threshold of the molecular mode is not well defined, and this is one thing that it's in discussion right now in the community. Okay, just to leave, for example, an open question. After to define the model in which we describe the system, we have two options to represent the Hamiltonian. One option is in coordinate space, and the other is in Hilbert space. In coordinate space, we have the kinetic operator, the potential energy surface, or the potential energy curve. And in Hilbert space, this part is given by the basis of the vibrational levels. As I mentioned, could be bound and unbound states of the Morse potential. The Hamiltonian of the field, harmonic oscillator, and the interruption Hamiltonian, that's especially the product between the field operator with the dipole moment function of the molecule. And one point to remark here is that we do not make use of the rotating weight approximation. We take into account the counter-rotating terms because we are interested in the physics at the strong and ultra-strong coupling regime. And in this coupling regimes, the counter-rotating terms takes importance in the dynamics. E sub 0 can be seen as the amplitude of the electric field, and lambda is the coupling strength between the light and matter, between the cavity mode and the molecular mode. However, not all systems behave similar, and there is one specific part of the Hamiltonian that drives the dynamics depending on the molecular species. This part is the dipole moment function, which that depending on the molecular nature of the dipole molecular nature will be obtained different dynamics in this hybrid system. In the Hilbert space, the dipole moment function is included in the Rabi state-dependent couplings. Okay. According to this, that different molecular species give rise to different dynamics or different spectrums in polaritonic systems. We define three different species of molecular or molecules in terms of the dipole moment function. We define polar molecules and non-polar molecules, which are given in terms of the dipole moment function at equilibrium position, and we define two types of polar molecules, which are given in terms of the slope of the dipole moment function. Positive is known as polar right, and negative is polar left. And all these molecular species can be modeled by the same dipole moment function, by the same functional form, just by changing the corresponding parameters. However, if we go to traditional ER spectrum, all these molecular species has similar spectrum. In other words, what are the transition dipole moments in the molecular dipole matrix? The difference of these molecular species come from the permanent dipole moments, which in the case of a polar right molecule, we have the highest values of the permanent dipoles in terms of the vibrational quantum number, and the functional form of this is looks like a Poissonian distribution. In the case of a polar left, the functional form and the vibrational quantum number is like an exponential decay, and for non-polar, I want to mention here that non-polar has the lowest values of the permanent dipole moments, and this is the key point to describe correctly this kind of system in different phenomena. Okay. For example, I will start with the spectroscopy of nonpolar molecules. Consider the Polariton spectrum of this hybrid system with nonpolar molecular species. Here I have two calculations in black I show the spectrum with the complete dipole matrix, considering the permanent dipole moments, and with dash red, and the red dash lines represent the spectrum neglecting the permanent dipole moments in number. As we can observe, only at the ultra-strong coupling regime in the Polariton spectrum, we obtain deviations from the result of the where we use the total matrix, the total dipole moment matrix. In addition, as we are working with molecules, we can measure or calculate observables of these molecular modes, and also observables of the cavity mode. And if we measure or we calculate, in this case, the mean bond distance of the molecular mode, we observe that if we neglect the permanent dipole moments, we obtain an idea that the bond, or as a bond hardening effect. However, in reality, considering the total matrix, which means avoiding one approximation, it's the opposite. We obtain bond softening of the bond distance, considering that these expectation values are for the ground polariton state. A similar case occurs for the mean photon number. However, for non-polar molecules, the mean photon number is low, below the one, and the deviation are smaller than in the case of the mean bond distance, in the case of the molecular part. One thing totally opposite is for polar white molecular species. For example, note here that for polar molecules, we obtain deviations even in the strong coupling, and notorious deviation in the spectrum. And also in the mean bond distance, we obtain the same result as in polar molecule. We can observe bond hardening effect when in reality is post-bond softening. But however, the ground state, the ground polariton state do not have only excitations in the vibrational excitations, also has vibrational radiation excitations. Note here that the mean photon number of the ground polariton state is around 10 as the coupling strength increases, and the difference, neglecting the permanent dipole moments, is huge in orders of magnitude. Okay, this is one point to consider, that we need to take into account the total matrix in this kind of system. Now I go from static properties to photodynamics, and the first example that I want to show is the self-dissociation of polar white molecular species. In this case, I choose the bond distance. I couple the bond distance of the hydrogen fluoride molecule to an infrared cavity, considering that this molecule is a polar white type. Here I have the potential energy curve of the bond distance of the hydrogen fluoride molecule. This is the function of the dipole moment. And first, I want to mention that all photodynamics, are performed using the multi-configurational time-dependent Hartree method, which is a very efficient method that considers a specific ansatz to solve, to propagate the wave function by solving the time-dependent Schrodinger equation. Okay. Before to explain what happened with this molecule inside a cavity, I want to explain what is the result if we use a continuous wave laser with a high intensity regime with this hydrogen fluoride molecule, just to make a to have a comparison point. After the subject, the hydrogen fluoride molecule with this continuous wave laser, the bond distance, and if we measure or if we calculate the mean bond distance, the bond distance increases as the molecule is continuously pumped. This means that the hydrogen fluoride molecule is vibrationally excited, and not only the mean bond distance increases, we can also obtain finite dissociation probabilities. But note here that the dissociation probabilities is measured or calculated in terms of the population of the bound state. Now, if we move to the case of the quantitative radiation, and we put the hydrogen fluoride molecule inside tumors or in a microcavity, and considering that the initial state is a diabatic state, that it is the direct product between the ground vibration state and the vacuum state, and that the coupling strength here between the molecule and radiation, it's analog to the high intensity regime. The molecule, without any other external source, also it's excited vibrationally, and also we can obtain finite dissociation probabilities without using any other external source, without using lasers. Here, I want to mention that this effect, that the blue line represents the effect of the dissociation, considering just one mode of the cavity. And this dissociation probability increase if we consider that the molecule can couple, although it's not on resonance, and although the first transition is not on resonance with the cavity, but the transition between higher vibrational levels could be on resonance with other modes of the cavity, which accelerates the dissociation of the molecule, as I show here with the red line. Okay, this is one new effect that we want to publish as soon as possible, and we are working in the new draft. And now I move to a test of this model with experimental results. In this case, we consider that the NO mode of sodium nitroprusside, which is a polar left molecule, is coupled with a Fabry-Perot cavity. We boiled the Morse potential and calculate by a simple calculation using Gaussian and DFT, a DFT calculation, a simple DFT calculation, just to have an idea what type of molecule or what type of molecular nation is the NO mode. And those are the points that we calculate, and this is the dipole moment that we use that give us the idea that it's polar left. And we consider in the model the total dipole matrix. Okay, here we have the experimental, the 2D infrared spectrum experimentally of the NO mode coupled to a Fabry-Perot cavity. And the horizontal lines represent the cuts that are shown here below, where the positive peaks represent transitions from the ground polariton state to the first branch of polaritons, I mean to the first lower polariton and to the first upper polariton, the hybrid states of the complete system. And also it can represent transition from the ground polariton state to the first excited vibrational state, just in the molecular mode. And the negative peaks here represent the transition from the first branch of polariton states to the second branch of polaritons. And the importance of this work, of these experiments, is that it is the first time that polariton to polariton transitions are observed. It's the first experiment where polariton to polariton transitions are observed. And also negative peaks could represent a transition from the first vibrational excited state to the second vibrational excited state. Okay. What we want to do to test if the model works well with real systems is to make a peak assignment of the spectrum. How we do this? Okay, from the experiment, we have the value of the fundamental transition. We have also the value of the excited state, the transition 1 to 2 and 1 over turn, the associated frequencies, and also we have the transition dipole moments, and the coupling between the subsystems, between radiation and matter. It's extracted from the linear polariton transmission that shows the lower and upper polariton, that it's around 46.5 wave numbers. We build the most potential, consider that the cavity is on resonance with the fundamental transition, put the coupling strength, diagonalize the complete Hamiltonian, and obtain the spectrum. And what we obtain? We obtain the following. We obtain that the polariton to polariton transitions match pretty well, or match with a good precision, just deviates only for a few wave numbers. And we can also predict what is the oscillation strength between these transitions, between these polariton to polariton transitions, and maybe why not other peaks in the spectrum are not observed. Just to finish this part of the talk, I want to mention that the chemical reactivity could change, that without any other external force, the hydrogen free molecule can be self-dissociated, considering unspecified chaotic state and for polar molecules, and that the peak assignment in non-linear spectroscopy, it's only possible if we consider in the model the permanent dipole moments. If we do not consider the permanent dipole moments, the peak assignment doesn't work well. Okay. Now I move to the part of the coupling to electronic transitions, polariton chemistry at visible regime. Okay. The key point here is that the cavity or the cavity frequency, it could be on resonance in electronic transitions. To have an idea of what's happening outside of the cavity, if a laser pump a lithium, in this case I changed the molecule, it's a lithium fluoride molecule, with the X UV pulse, we create a copy of the ground vibrational state in the first excited electronic state, as is not an eigenvalence state of this electronic state will evolve, will reach an avoided crossing that expression between these sigma states, and some part will dissociate, and another part will go to a returning point and will be oscillating between this part, creating packets of dissociation. This is the picture out of the cavity. And now what happened inside the cavity? What happened if we put this molecule inside the cavity? The new point here is that we have different electronic states. We have more than one dipole moment, but we have these terms that are the non-adiabatic couplings that transfer population at the avoidant crossing position. And also, if we are considering that we are in the visible regime, we create, or it is created, another crossing that is known as line-induced crossing at the position where the cavity frequency is resonant between the energy difference between these two electronic states. Okay. The mechanism is the following. We start exciting the molecule with HUB pulse. The weight packet evolve in the electron excited state, reach the line use crossing, has an splitting, and the part that continues in the excited electron state continue until reach the avoiding crossing, and some part will dissociate eventually. This part that it's in the ground electron state will bounce back and forth between these two returning points, making transition to the excited electronic state that eventually will go again to the dissociation. This can be seen as a cycle here, as a continuous cycle until all the weight packet dissociate. The point here is that we can control the dissociation of lithium fluoride molecules, creating packets of dissociation. If the lithium fluoride molecule is coupled of this position, is on resonant. The cavity frequency is on resonant. The gray line represents the dissociation outside of the cavity, and we can observe the blue line considering this position. We have packets of dissociation. We can make some control over the dissociation of this molecule. If we increase or decrease the cavity frequency, we move the position where the cavity is on resonance with these two electronic states, and the period of these packets of dissociation increase or decrease depending on the case of the cavity frequency. This is the first example to make control over the dissociation. The next case is a discussion of the network. Is a discussion between what happened with these molecules with quantum fields, and what happened if I consider, instead of quantized fields, classical fields. When I mean classical fields, it's continuous wave lasers with the same frequency of the cavity frequency. There's a discussion that the photodynamics is the same, and okay, at some part it's the same, but however, can we obtain the same dynamics by implementing continuous wave lasers instead of a cavity? Well, the answer at some part is yes, and for another part it's maybe not. And in the weak and maybe low strong coupling regime, the dynamics is exactly the same if we consider a cavity of continuous wave lasers. However, if we start to increase the coupling strength, we observe that there are some parts that are equal, but another part that deviates from the classical part to the quantum part. The answer is that the part that it's the same, it's the part that it represented, or the transitions that occurs in the line use crossing positions. But the positions that occur, the transition that occurs in the avoided crossings are not the same. And what is the reason? Okay, from a perspective of the potential energy surface, the complete potential energy surface is the mix of the potential of the molecule, the harmonic potential of the cavity field, and the dipole moments involved in the dynamics. If we increase the coupling strength, we modify all these potentials, and as a consequence, in the avoided crossing, the position of the avoided crossing, everything could change, and the transitions are not the same. And that is the reason why the quantum dynamics deviates from a semi-classical quantum part. In addition, we can, for example, calculate the population at a given time of the vibrational levels in the ground electronic state, and we can observe that then there is a shift between the classical and the quantum part. That is a future that the potential surface are modified. In addition, also, we have two photon transitions in the quantum case, which is represented by the peak in this position close to 1 electron. Okay, this is the discussion about quantum versus classical fields. And finally, one of the other parties, is there any way to know that the line use crossing are real? Okay, in this work, in this paper, we propose an experiment to reveal the presence of the line use crossings. The mechanism is the following: a molecular beam shoots molecule by molecule, assuming that we can shoot a molecule by molecule, enters to the cavity, or before to enter to the cavity, we excite the molecule with the XUV palm laser, which goes to the excited electronic state, and the molecule enters to the cavity. It's coupled to the quantum radiation, which generates the line use crossing, and at some point, the portion of the wave packet that is in the ground electronic state will move between these two returning points. But at some time, we can send a pulse laser. This laser should be, according to the difference, to the energy difference, should be an infrared laser and it has a polarization that couple a sigma state with a pi state in order to do not interfere with the polarization of the cavity field that excites this portion of the packet to the pi state. And as these two portions of the wave packets goes to dissociation, assuming that the pi state is completely dissociative state, at the end we can measure two kinetic energy release, one from the provided by the infrared pulse and another provided by the UV pulse. And if we can perform this experiment in the laboratory, we can detect this kinetic energy release, and it's a measure or it's an indication that that the line use crossings are real in this kind of hybrid systems. I here have two examples, one from a cavity, the cavity frequency resonance at a specific point and another point that depends also on the time delay of the broad pulse. But it is a measure that we can make to predict, to assume that the line use crossings are real or are created in this kind of hybrid systems. The conclusions are the permanent dipole moments of these molecules produce asymmetries that modify the potential surface, and as a consequence, the photodynamics quantum is not at the same classical part. We can make some kind of control of the chemical reactions, as for example, dissociation of the lithium fluoride molecule, and some observables can be measured to reveal the presence of the line use conical interception. Thank you for your attention. This is my group by now, the group of Professor Polariton here in Santiago de Chile. Thanks to the funding funded by the postdoctoral fellowship here in Chile, and MIRO, the Millennium Research Institute, the Millennium Institute for Research in Optics here in Chile. The collaborators around the world for theory, my PhD advisor, Jose Luis Sainz, Federico Hernandez, who was a postdoc here in Santiago. Now he's in London. And experiment and the people from the Naval Research Laboratory in USA. And thank you for the attention.
Thank you very much, Dr. Triana. It's a very interesting topic. So now we will move on into the question session. For that, please click the raise hand button, which is in the participants window. Then I will let you know when it's your turn to ask. Another way is to let us know through the chat. For people who is watching us on YouTube, they are also able to ask questions through the chat box. So let's start. We have 15 minutes. Doctor Gabriel Merino. Doctor Merino, you can turn on your microphone.
Ya suena ya se escucha ya, ¿verdad? Okay.
Sí.
So I have a couple of questions. The first is that if these models could be applied to any type of cavities like fullerenes or nanotubes.
Do you mean if maybe nanotubes can be introduced in this kind of cavities?
Yes, there are some nanotubes that are not too long. So basically, if you put a molecule inside.
Yeah. For example, maybe not exactly a Fabry-Pérot cavity. Maybe not, depend of the length of the molecular system or the solid state system. But there are another kind of systems, for example, like this one, that it's a plasmonic nanocavity. You maybe can put the system, the molecular system, inside this kind of systems. There is the only thing is to boil the cavity or the plasmonic system in a way that the frequency that you generate is on resonant with some particular mode of the nanotube to maybe to increase the efficiency of the phenomena that you want to observe.
Okay, great. And my other question is if can this model be applied in this area, this new area that it's called mechanochemistry? Because basically in mechanochemistry, you create some cavities, perhaps are not permanent, but basically you have these cavities, and it's quite interesting that using these new techniques, the reactivity of the molecules changes drastically. So I don't know if you can mix these models to try to explain what is happening there, no?
I don't know the field. I can admit that it's a new word for me in mechanochemistry. I don't know exactly if it could be applied well or not. I do know the mechanochemistry field.
Okay, gracias, Johan.
Okay.
Is there any other question? Well, so one more time, we thank our speaker, Dr. Johan Triana, and the entire audience for joining us today. Remember that we will have a webinar in 2 weeks. All the information will be available in our social networks. See you soon, and thank you all again. Thank you again, Johan Triana.
Okay, thanks for your attention.